You are all welcome to the seventh unit of our lecture series on algebra, and today I'm taking that of series and sequences. And at that we have 5 simple things to do. We want to know the definition, the differences, the types of series and sequence, formulas, and then we work some examples, and that'll be it. But before we dive into that, I want us to have an intuition of what series and sequence is all about. If you look at the images I have on slide 3, you could tell a story. You could tell that there's an arrangement of things. So I have as arrangement of things here. Arrangement of things can be in a form, we can term them as objects or elements. And what comes to mind when you hear the word element? Sets. So we've already done set theory. So realize that everything is coming back to play. In this arrangement, there's a particular pattern. If I should sow a seed, it takes a pattern to grow. It doesn't make certain stages. The second image is how we grow. We are being born, we become adolescents, we go to adulthood and wahalas and all that, and we grow old. If you are building a story building, you first have to clear the land, you get your foundation done. You can't tell me you can lay the 4th floor without a foundation being done. No. So there's a particular pattern, there's an order. So let me use the word order of arrangement. The last image has to do with how bacteria grow. They have a curve they follow. So from these images we have a fair idea of what we should expect in our series and sequence. So I have here as a remark from the image, I saw a pattern or an order of things. In this way we have the sequences. So sequence are arrangement of objects or elements in a particular order. If I sum up this object, then I get a series. I hope it's not confusing. So sequence is just the arrangement of objects, and then series becomes the addition of the sequences. So if you look at the example I have in slide 4, 1, 4, 9, 16, 25 is a sequence. They're separated by commas, and then it follows a pattern. We'll get to understand the pattern later. This example is also a sequence because from 1 in the counting order, from 1 I go to 2, I go to 3, 4, 5, 6, and so on. I can even have A, B, C, D, E. This is also a sequence. It is in a particular order we know. You can't say A, C, E, no. If I move to the next example, it is separated by commas, but this is not a sequence. Why? I don't see any pattern of the arrangement. 1, 9, 25, 6. It is not ordered. The last example is also not a sequence. I've already explained why. There is no pattern, or there's no order. I can't tell what is happening, so it is not a sequence. So you get to know this. Now when we come to the series, we said series is addition of. So this is a series, I'm adding the sequences. This is also a series, this is also a series. Now look at something here. When I'm taking this particular example I want to draw, I've written it in 2 forms. In whatever situation I sum it up, I'm getting 10. There's something you must note here. It means the order does not really matter in series because I'm summing. 1 plus, in fact, 1 plus 3 plus 2 is 6. 2 plus 1 plus 3 is 6. 3 plus 2 plus 1 is still 6. So that's the interesting thing about series. We don't care how the order is. But if it were to be sequence, I'm really interested in the order. That is the main difference. Okay, so I've already talked about the differences here. The order is important for sequence, the order is not important for series. And in a general form, you want to write it as this to tell me that it is a series. Anywhere I see summation, I know I'm summing up, and that becomes, I think I misplaced their names. The first one is sequence, the second one is series, because I see a summation sign there. Okay, and that is as simple as that. Now let's move to the types, and then we work some examples and we are done. There are so many types of series and sequence. There are ones like arithmetic sequence, geometric, harmonic, Fibonacci sequence. If you're in the mathematical department, you will hear of Fibonacci sequence. But in our field of specialization now, we will consider two main aspects of the types. We'll just take the two, the common one, arithmetic, and then geometric series and sequence. Again, series are in a pattern with commas. No, sequence are pattern of objects, series are addition of the sequences. If I'm looking at arithmetic, there's one thing that should come to mind, and that is the differences, the common difference. And the geometric is a ratio. I find a common ratio, and what do I do to the pattern? I either add or I subtract from the pattern. But in geometric, I multiply by them to see or observe the sequence. Is that simple? Let me just put it that way for you. So let's take an example here. Someone will say, how do I find this common ratio or differences? And that leads me to my next slide, slide 7. We are given a sequence. This is a sequence. Why? Because there's an order. It follows a pattern. Realize that if I take 1 and 4, the difference is 3, 4 and 7, this and that, 13 and 16, the difference is 3. The difference is 3, and that is how we find a common difference. We subtract 4 minus 1 is the same as 7 minus 3, 7 minus 4 is the same as 16 minus 13. So it's as if you have an minus 1 minus the an. Or another way, if you want to follow the usual pattern, this is a1, a2, a3. So it's always an minus that, and then you have the common difference. And then the general way I've given us equation 1. If I keep adding the terms up, so it says don't bother about the sequence. Take the first number, add the d to it, and the next step add 2d, add 3 of it, and then you add n minus 1 of it. It's a recursive form, so you follow the pattern. I just need the first number and I can produce the other sequences. As simple as that. Now look at the next one, 1, 7, 10. It says what is the common difference? I can't find the common difference. No difference, because this is not even a sequence in the first place. There's no pattern. So that's how smart you must be. Okay, else you waste time thinking through. Now let's take the common ratio. This is a sequence. There's a particular pattern, but that pattern does not give me a common difference, but it gives me a common ratio. How? Look at it. 3 over 1 is the same as 9 over 3, the same as 27 over 3, and so on and so forth. So ratio means something over something, and this gives me 3. Hence the common ratio is 3. If I want to generate a sequence, it says take the very first one, multiply the first one by the r, multiply by r square, multiply by r cube, then the last pattern becomes n minus 1. If I take the first number, I need the first number, I need my common ratio, I can generate the sequence. As simple as that. And so that is what I have in equation 2. So note the general form for me. In the next example, it says find the common ratio. Can you find the common ratio of this? No, because it is not a sequence. There's no order in this, there's no pattern. So let's prove this. 9 over 1, 27 over 9, 3 over 27. There's no equality here, and so there's no common ratio. All right, now to the formulas. In using the formulas, I always say we are the end users. There are ways to prove this. We've already gone through the end term. We want to have two common formulas: the end term in a sequence and then the sum of terms. We've seen this formula already. What was it on? It was on the arithmetic sequence. I can see the common difference D. We saw the common denominator difference, and so there's a sum of squares for arithmetic as well. Okay, so it says the A1 and then the AN. In the next formula, we've seen this guy already. It was on the geometric. So that is it for the end term, and if I use this, I'm using the geometric sum of terms. This is just the two formulas we need for each of them. That is it. So you take note of it for me. Again, you already know what A1 is. A1 is the first term. D is the common difference. R is the common ratio. What else? N is the nth term. Sn is the sum of terms. We are looking at the sum of terms. I think that is all for now. So quickly, let's take examples. I'll take 2 examples each on arithmetic and that of the geometric, and let's see what we'll have afterwards. In example 1, we are given a sequence and we asked to find the common difference, the nth, 21st term. Because of the questions being asked, automatically you know you are finding the arithmetic progression. But if that wasn't given, how would you know it is AP? So I'll use AP for arithmetic and then GP. I could say 7 minus 4 is the same as 10 minus 7, the same as 30 minus 10, the same as 60 minus 10. All gives me 3. But if I take it as 7 over 4, 10 over 7, 13 over 10, they are not equal. So it means that I can't even use the geometric ratio, and hence the common difference is 3. To find the nth term, we've already seen this formula here. So I do a quick substitution. A1 is the first term, 4. D is 3. So if I expand this, I have 4 plus 3n minus 3, and that gives me 3n minus 3, and that gives me 3n plus 1. That is my nth term now. And the 21st term means that wherever you see n, you substitute 21 into it. And so I have 3 into bracket 21 plus 1. That gives me, I'm not so sure of the answer. But this is how simple it is. Okay, it means that if your nth term is wrong, your 21st term, you are looking for 21st term in the sequence. It says it is 64. But originally we're given 1, 2, 3, 4, 5, 6, 7. We're given just 7 terms, and you realize that we can even find the other term. The 21st term is 64, and that is how we find. If I want to find the 8th term, it means wherever I see n, I substitute 8 into it. Okay, now let's take the second example. I'm giving a sequence. It says arithmetic sequence. It is just obvious for you, but for the weaker brethren, let's see. I'll first do the subtraction. 16 minus 12, 20 minus 16. I get 4, I get 4, I get 4. Okay, let's take the ratio. 12 over 8 and then 16 over 12 and then 20 over 12. There will be no equality here. 12 over 8 is I think 6 on 4, no, 3 4 12. No, the common divisor is 2, 6 and then 4. They will never be the same, so I can't find the common ratio, but I can find the common difference, and that is 4. The n term I've already given. The n term is a plus n minus 1d. So let's do substitution. My first term is 8 here. The d is 4. I expand, I get 8 plus 4n minus 4, and that gives me 4n plus 4. 4n plus 4. Okay, so that is my n term. But we asked also find a sum of terms, so I choose this formula, and by substitution now an I've already found it, so I bring it here. 4n plus 4. You expand and then you simplify, so I'll leave it here. Simplify means you group like terms. Oh, I was prompted the red pen is not so cool, but I keep using it. Forgive me. Let me help with the expansion. N on 2, 8 plus 4n plus 4. That gives me n on 2, 12 plus 4n. You can simply expand this, or you leave it this way. It is still correct. Okay, and that is it. I said I'm going to solve just 2 examples, but permit me to solve the last example under AP. Again, in this example, I'm interested because it's no more sequence, but it is given as series. Why is it series? I see the sum. It is no more commas. If it had been 1, 8, 15, I tell it's a sequence, but there's addition, so it means I'm adding up. What was the question itself? Let me stay on slide 11. We're given some information. It says the sum of the series is 369. How many terms are in this series? That's an interesting thing to look at. I'm given this information, how many terms, but I know that Sn is given as this formula, where An is given as this one. So let me do my arrow. How do I find A1? A1 is 1 plus n minus 1. The common divisor, why do I keep using divisor? The common difference is 7. You can check that. So I have 1 plus 7n minus 7. That gives me 7n minus 6. Am I right with this? Yeah, that is it. So I can now substitute A1, which is still 1 here, plus An. I had 7n minus 6. Then I can expand. Don't forget Sn has been given, so you don't forget that number. N on 2. This is going to give me 7n minus 5. I'm very careful with my addition and subtractions. I can group like terms, multiply this by that, and then I'm going to get 792 is equal to n. 7n minus 5. I can expand and get 7n squared minus 5n equal to 792. I can group, or let me just say I can move everything to the other hand. Have 7n squared minus 5n minus 792 equal to 0. What do you see here? This is a polynomial. We saw set, now we are seeing a polynomial. This is of degree 2. So it is quadratic. I'm referring back to everything we've learned. It is quadratic. I can factorize this one. There's no division here. I can factorize it into 2 if I have, or if I know them. In factorization, we will have 7n plus 72, and then n minus 11 equal to 0. This means I have 2 answers for n. You know that. And then you ask yourself, which one do I choose? Which one do I choose? They are all correct, but which one do you choose here? Because we are looking at the number of terms, it is a counting. We are counting, and hence I can't use fraction, but I can count to 11. So I use the n equal to 11 as my answer. So I have 11 terms in the series. Okay, so you take your time and you go through the expansions, and then you'll be fine. Okay, so that is my last example on the AP. All the other examples I wouldn't touch it, but you can pause the video, look at the question, and then try and solve it. I have the answers provided in the slides. Okay, so I didn't solve example which one? I didn't solve example 2, so you can pause them and then go through. Now let's quickly move to examples on GP. I think 2 examples will do. We are given a sequence. We have to find a common ratio. As far as I see the word ratio, something should ring a bell, something should click. I'm looking at GP. How do you find the ratio? I've already gone through so many examples. I divide a term by term, and you realize that all the term will be difference of 4 or ratio of 4, and so that's my common ratio. But I'm asked to find the 9th term. For GP, this is the n term formula, so you must know these formulas. And I do a substitution. The 9th term means wherever I see n, I substitute 9. A is the first number, which is 4. R, we had 4. A is 1, the first number 1. R is 4 to the power n minus 1. So 4n is 9 minus 1. 4 to the power 8, and then you know this answer. What do you see here? This is indices. Yeah, this is indices. It means our GP is in the form of indices, because it's raised to some index. This is an indices because I have the base raised to the index n minus 1. Let me not even go there. Okay, and so that is it for your 9th term. It is 6, 5, whatever. This is calculator work. Okay, I hope I'm not rushing through. Let's take the second example on GP. First, you read the information and then you extract. It says the 5th term of a GP is given as that, so this is my first information, and the 8th term is also given as that. I have my second information. Find the series. Find the series, and then I'm sure you'll be shocked and ask, how do I get a series? But you can find a series because the important information is given, and because you know it is a geometric progression, we can find the series using this formula. This is the n term formula. We are not using the sum because we are not finding the sum of terms. We want to find the series. So by substitution, wherever I see n from equation 1 and 2, it means A5 is AR on 4, A8 is AR on 7 by the n term formula. So I can now equate them to their values and represent them as equation 1. Already I have equation 1 and equation 2, so let me use equation 3 and equation 4. I equate them to the values which was given 162 and then 4374. let me use the blue one to indicate which ones I'm equating. Now I'm equating this guys to this. When it gets here, it's up to you to how you want to solve it, whether you want to add the equations, you want to multiply them, you want to subtract them. The most important thing is to find the terms we need. So I chose to divide them. I divide equation 4 by equation 3. I've changed the marker to blue. I'll have this. You can easily verify that by indices. I have r to the power 7 minus 4. I hope you've not forgotten that. And I have this will give me r to the power 3 equal to the division here by calculator. I get 27. Again, by indices in this section, because I want r, I need to find something such that if that is raised to the power 3, I can easily equate them. And funny enough, I have 27 is 3 to the power 3, and by comparing, I get r equals 3. Realize we've employed indices, we've employed polynomials, everything we've done in the previous lecture series. If I have 3, I can find a. How do you find a? It means I can substitute a into any of the equation. Substitute a into, let's say, equation 3. From equation 3, we had a r to the power 3 is equal to 164. It means a is equal to 164 over r to the power 4. We've already found what r is, so by substitution you should be able to find a value for a, and then I use this to find the sequence. But the question says find the series. It means there's something wrong with this. The right answer should be a plus ar squared plus arn minus 1. This is the right thing to do, and that is how interesting series and sequences are. For my substitutions, I had a to be 2. You can verify that for me. Okay, now to the problem of the day. Today I have 5 problems. And what are we required to do? Pause the video and then see what you can do. For this, I want you to check whether the problems are arithmetic progressions or geometric progressions. Just read them. I've provided my answers. I think question 1 is geometric, question 2 is arithmetic, question 3 is geometric, question 4 is arithmetic, question 5 is arithmetic. Just read, and then if there's something to argue about, the comment section is for you. Let's see how smart we can be with this question. And that brings me to the end of my series and sequences. We'll look at unit 8, which is permutations and combination. Thank you very much.